Hey everyone, and welcome. Today we are diving deep into one of the most fundamental, most powerful shapes in all of geometry, the triangle. But right off the bat, I've got a question for you. Think about it. No matter how big or small, skinny or wide a triangle is, there's this one, magic rule that every single one has to follow. Any ideas what that could be? Well, hang tight. We're going to find out. All right, so let's build this thing from the ground up. We're starting with the absolute basics. First question, what actually makes a triangle a triangle? Well, the clue is right there in the name, tri. That means three, right? So you've got three straight sides, three angles on the inside, and three corners, which have a fancy name, vertices. It's really one of the most basic, simple shapes you can possibly draw. And that right there, that brings us back to our magic rule. So what was the answer? It's 180 degrees. Yep. If you add up the three angles inside any triangle, I don't care which one, the total is always going to be exactly 180. That's like a core truth of geometry. It never changes. Okay, so we need three sides. Got it. But does that mean you can just grab any three lines and stick them together to make a triangle? Let's think about that. And the answer is a big, firm no. And it's all because of this rule called the triangle inequality theorem. It sounds complicated, but it's not. All it says is that if you take any two sides, their lengths added together have to be longer than the third side. So picture this. You've got sticks of length 3, 4, and 8. You try to connect them, it won't work. The 3 and 4 sticks together are only 7 units long. They're too short to reach the ends of the 8 stick. But if you add sticks of 3, 4, and 5, that works perfectly, because 3 plus 4 is 7, which is bigger than 5. Okay, so we know the basic rules. Now let's get into the fun part, giving them names. It's time to meet the different members of the triangle family because they are not all the same.
Basically, we can sort any triangle in two main ways. First up, we can look at its sides. If all three sides are equal, we call it equilateral. If just two sides are equal, it's an isosceles. And if all three sides are different lengths, that's a scaling triangle. Simple enough, right? The other way is to look at the angles. If all the angles are small and sharp, less than 90 degrees, it's acute. If it's got that perfect square corner, a 90-degree angle, it's a right triangle. And if it has one big, wide angle, more than 90 degrees, we call it obtuse. You know, out of all of them, the equilateral triangle is the super special one. It's like the perfectionist of the family. Not only are its three sides perfectly equal, its three angles are always exactly 60 degrees each. 60 plus 60 plus 60, 180. Perfect. And because it's so symmetrical, if you draw a line from any corner straight down, that one line is the height, the median, and the angle bisector all at once. It does three jobs. It's pretty cool. Okay, let's move on to measuring these things. We're going to talk about how to find the distance around them, the space inside them, and we're going to get to maybe the most famous rule in all of math, for real. So how do you find the area, all the space packed inside a triangle? It's actually a pretty simple three-step deal. Step 1, pick any side you want and call it the base. Step 2, from the opposite corner, you need to find the height, which is a line that drops straight down and hits the base at a perfect 90-degree angle. And finally, step 3, you just use the formula. Area is 1/2 times your base times that height. And here's a weird little fun fact. With those wide, obtuse triangles, sometimes that height line actually lands outside the triangle. Kind of strange, but the math still works. And the perimeter? Oh, that's way easier. Just think of it like putting a fence around a triangular yard. All you do is add up the lengths of the three sides. Side 1 plus side 2 plus side 3. Done. Okay, deep breath, get ready, because what we're about to talk about has been called the most widely known, most loved, and most useful rule in all of geometry. That's a huge claim. Any guesses what we're talking about? Of course, it's the Pythagorean theorem. Now, here's the number one thing you have to remember. This rule only works for right-angled triangles. That's it. And the formula itself is an absolute icon. A squared plus B squared equals C squared. Here, C is always the longest side, the one across from the right angle, which we call the hypotenuse. And trust me, this isn't just some dusty old formula from a textbook. It's the backbone of construction, architecture, even the GPS in your phone, an absolute legend of a theorem. So what happens when you have two triangles and you want to compare them? Well, there's a really easy way to think about it. Just ask yourself, are they twins or are they cousins? So congruent triangles, they're the identical twins. They are a perfect copy-paste of each other. Same shape, same size, everything.
Similar triangles, on the other hand, are like cousins. They've got the same family look, the same shape, same angles, but they're different sizes. Think of it like a big photograph and a small wallet-sized print of that same photo. Same picture, different sizes. So how can you be sure two triangles are identical twins without having to measure every single side and every single angle? Well, lucky for us, there are shortcuts. For example, if you can just prove that all three sides of one match all three sides of the other, that's the side-side-side rule, then you're done. They have to be congruent. And there are a bunch of other combinations of sides and angles that work just as well, like side, angle, side angle, and so on. And proving they're just cousins, similar, is even easier. All you need is the angle-angle rule. If you can show that just two angles in one triangle match two angles on the other, they are 100% guaranteed to be similar. Why? Because if two angles match, that third one has to match too, right? Because they all have to add up to 180. The other way is to show that all their sides are in the same ratio, meaning one is just a perfectly scaled up or scaled down version of the other. Okay, for our last section, we're going to go inside the triangle. We're going to uncover some of its secrets, these hidden lines and special points that have some really powerful properties. So here's a really neat trick. It's called the exterior angle theorem. If you take any side of a triangle and just extend it out, you create a new angle on the outside, right? Well, that outside angle is always equal to the two inside angles that are way over on the opposite side added together. It's a super handy shortcut if you're trying to figure out missing angles. Next up is the median. This is a really simple line, but what it does is pretty amazing. You just draw a line from one corner to the exact middle of the opposite side. And boom! Just by doing that, you've perfectly split the triangle's area into two equal halves, every single time. So what happens if you draw all three medians? Well, something cool happens. They all cross at the exact same point. And this point has a special name, the centroid. And this isn't just some random intersection. It's the triangle's center of gravity. I mean, if you cut a triangle out of cardboard, you could literally balance it on the tip of a pencil right at the centroid. It's the perfect balance point, which is why it's so important for engineers. Oh, and it also does this other neat thing. It cuts every median into a perfect 2-to-1 ratio. Okay, our last little secret for today is the angle bisector theorem. An angle bisector is just a line that takes one of the corners and slices that angle perfectly in half. But here's the cool part. When that line hits the opposite side, it splits that side into two pieces, right? Well, this theorem says that the ratio of the two other sides of the triangle is exactly the same as the ratio of those two little pieces you just created. It's this beautiful, hidden proportion built right into the triangle. So there you have it. We've gone all the way from the absolute basic definition of a triangle to uncovering its internal secrets. We've seen the rules that give it its shape, its size, and its power. But remember, everything we've talked about is just for one triangle. The real magic, the real power, starts when you begin putting them together. That's how you get the stable structures of bridges, the beautiful facets of gems, and really the building blocks for almost any complex design you can think of. But that's a story for another time.